ठीक है सर।
सब ठीक है, सब बढ़िया है, सब समझ में आ
ये,
रहा है।
यस सर।
ओके। अंकित, बॉबी, हरजोत, आदर्श,
यस सर।
क्या है तुम लोगों का रिव्यू?
अभी तो सही चल रहा है सब तक तो।
यस सर, अच्छा चल रहा है।
अच्छा चल रहा है, ठीक है।
हाँ यस सर, अभी तक तो आ रहा है समझ। सही है।
कोई कंप्लेन, कोई नाराजगी? नहीं है?
नहीं सर।
चलो अच्छा है। अच्छा, कौन कौन है तुम अभी क्लास में, कौन कौन? I can't see this. So, okay. ठीक है, fine. So a little bit, what we will do, a little bit of recapitulation, but not with the name of revising what we have studied. Okay, so okay. So one uh, type of, so before going to the way of how polymer deforms, let us revise a little bit about their basic difference from the conventional kind of materials which we study, which is mostly metallic materials. And fortunately or unfortunately, even in metallic materials, we usually study the ferrous materials. So not so much of information is given on materials like copper, nickel, aluminum a little bit, because there are industries serving that kind of material. But other materials are less studied, and it is like Darwin's law that the organ which is less used will be less evolving. So those materials which are studied less, there also research and understanding of those kind of materials are also less. So there are various reasons to study certain material. For example, you study steel because the applicability is maximum, and you look around and you will find in previous days you would have seen almost everything made up of steel around you. But today, if you look around, you will find plastic everywhere. So polymeric material. And there are other materials like uranium is there, which is used for certain specific purpose. And because of that, people have studied that in depth. But for example, in the steel industry, you use a lot of alloying elements. For instance, molybdenum, niobium, vanadium, tungsten, chromium, and tantalum and others. But you don't study the extraction of that. You don't study the structural property, crystal structure, physical metallurgy, and other things, or phase diagram of those materials. Because they are not used directly for the application, they are just used in the steel as an alloying element. So, जैसे मसालों के बारे में ज़्यादा नहीं पढ़ते हैं, वैसे ही वो एलिमेंट्स के बारे में ज़्यादा स्टडी नहीं हो पाती. So, so if we just talk about polymers and metallic materials, so then what difference do you see? Can you describe three differences between metallic materials and polymeric materials, which you can observe? Any one of you? तो थोड़ा इंटरैक्टिव करना पड़ेगा, अदरवाइज लाइव सेशन का तो कोई मतलब नहीं है. तीन डिफरेंस जो तुमको दिखता है एक पॉलीमरिक मटेरियल में और एक मेटालिक मटेरियल। आदर्श, हरजोत बताओ।
सो पहले तो मतलब पॉलीमर्स में जो होता है ना कि एमॉर्फस का कंट्रीब्यूशन ज्यादा होता है।
ये तुमको
और
दिखता है?
नहीं मतलब होता है सर, मतलब
नहीं
दिखता
सर,
है।
आई एम आस्किंग व्हाट डू यू सी, व्हाट डू यू ऑब्जर्व? बुकिश डिफरेंस तो बहुत सारा मिल जाएगा। The two abundant material which you see around you are metallic materials and polymeric material. तो ऐसा क्या डिफरेंस दिखता है तुमको?
मेटालिक मटेरियल्स ज्यादा हार्ड होता है।
ज्यादा हार्ड होता है, ज्यादा स्टिफ होते हैं, इट इज
यस
नॉट
सर।
पॉसिबल टू डिफॉर्म देम इजीली।
यस सर।
Praveen is saying weight difference, ठीक है, that is also true। दो
सर
हुआ
पॉलीमर
और
ब्रिटल होता है,
हाँ।
और
मेटल डक्टाइल।
लुमिनेंस।
हाँ आदर्श क्या बोल रहे हो?
सर पॉलीमर ब्रिटल होता है, मेटल डक्टाइल।
ये कैसे पता चलता है तुमको?
सर जैसे मेटल को मीन्स वायर में हम लोग बना सकते हैं,
हाँ,
लेकिन चूंकि मतलब पॉलीमर का एमॉर्फस नेचर होता है तो, और वो थोड़ा सा मतलब मेटल से कम हार्ड होता है, तो उसको हम लोग वायर में उतना इजीली नहीं बना सकते एज कम्पेयर टू मेटल।
ये पूरा पूरा सही नहीं है। हरजोत,
ये
what were
यस।
you saying?
सर लुमिनेंस।
What?
लुमिनेंस लाइक मेटल्स शाइन कर, जो नेकेड आई से दिख जाता है, एंड पॉलीमर्स ज्यादातर शाइन नहीं करते।
Okay. So that is also not completely true. So color and optical effects can be given. So as long as we're talking about optical light, other lights, X-ray and UV rays and those kind of lights, there will be difference because of crystal structure of metallic materials and polymeric materials. But optical light reflection can be created by using dye or coloring agents in the polymers as well. So, but metallic effect आएगा नहीं आएगा, आ भी सकता है, but I am not an expert in that area. What Adarsh was saying is a very vague term to define that, but you can use those kind of terms. But polymers are not necessarily actually. If you see, polymers are in on average they are ductile in comparison to metallic materials. Okay, they are not very stiff and they are also very ductile. So wire, so एक application हो गया, you make wire of metallic materials first because they are conducting and polymers are not conducting. Even if they conduct, if heat is generated because of resistance heating, polymer material will be changing their molecular structure. Metallic material will not be doing that. So that is one reason why you make wires from uh, metallic material, but that is conducting wire. If you want to make wires for other applications uh, like for bridges, hanging bridges, so there again the stiffness of the metallic material is being used to make that kind of wire, which you can't get in polymers. Right. So that is one thing. What one of you said was weight is one of the important thing which makes the polymer dominate in today's world. And another reason why polymer is kind of dominating and it has kind of ripped. So even if you talk to steel industrialists today and ask them, what is the material which can replace steel in future, they will be very hurt with this question, and they will say there is no material which can replace this. But it has been replaced. Steel has been replaced, and it is out of your table because of polymers. And the reason why that has happened, because so why steel was dominating, because steel is one alloy where you can mix different kind of alloying elements and you can get different properties in one. So you usually study iron carbon diagram, but iron carbon diagram is just an example of plain carbon steel, right, where you only have carbon. But by putting different alloying elements, you can alter the behavior. So you can make, for instance, austenitic stainless steel, which is at room temperature, austenitic, and therefore it will be non-magnetic. Okay, and then you can make magnetic, so you can use the magnetic property of that. And then you can put a lot of alloying element. For instance, you can put 18% manganese in iron, and you can make a steel which is martensitic without having any carbon. So you can make interstitial free steel where you don't have any interstitial atoms in the steel. So you don't have carbon, nitrogen, or boron, and that makes the steel much more ductile in comparison to other grades of steel. So that was the advantage, that you can make, and you can tweak here and there a little bit, and then you can change the property to an extent. So you can start from a yield strength of 150 megapascal, and you can go to a yield strength of 1200. You could go to a yield strength of 1200 megapascals in steels, but now you can go to 1 GPa as well. So you're kind of touching the theoretical cohesive stress or strength of a material, and not by making single crystal. In polycrystalline steel, you can still achieve this. Okay, so that is the range, not just in the yield strength, but in other properties. So you can make conducting steel, you can make non-conducting steel, magnetic steel, non-magnetic steel. You can make, you can do a lot of variations there, and that was one of the things why steel was dominating, and that is the advantage with polymer as well, that you can make a very stiff polymer like ABS, or you can make a very ductile polymer like nylon. You can make polymer which is, so why? Because polymer is giving you a different combination. So you can have a material where you can change the crystallinity, the degree of crystallinity. You can change the amount of stiffness by changing the molecular weight. And there also you have two types of variation. You can change number molecular weight, you can change weight average molecular weight, right? And you can, by just tweaking the right molecular structure, you can actually change, in molecular structure, you can also change a lot of things, right? So you can make isotactic, atactic, syndiotactic, or you can change the side groups. So you can put something there, or you can put a benzene there. And just like steel, you can do a lot of variation in the polymeric structure. And so if you kind of put this kind of heavy side groups, then you avoid the rotation. So the rotation will not be possible because of steric hindrance, and because of the atomic structure and electronic configuration of these atoms, they maintain certain angle with each other. Okay, and that requires or demands them to rotate or not rotate. So the possibility of rotation along this axis is limited when you have heavier atoms or molecules on the side groups in comparison to if you just have hydrogen. Okay, so you are getting a lot of degrees where you can, degrees of freedom where you can change some things. So you are getting a lot of options to change. So you can obviously change the length of this, right? So that will be one monomer can be longer, a very, very long chain, or you can do branching. Okay, you can do branching, and in that branching you can maintain random pattern, you can maintain certain kind of ordering pattern. Apart from that, what else you can do is you can put the polymer at so below glass transition temperature. if you plot volume, and then you can solidify it at a crystalline, in the crystalline part, or in the amorphous part, or by changing the strain rate or cooling rate. You can put it in a place where, or at a temperature where it is certain percentage of the polymer is amorphous, certain percentage of the polymer is crystalline. So you see that you can change a lot of things, and thereby you can make different kind of polymers. So you have hard polymers also. Like if you see the bottles, so uh, not that water bottle which you get at railway platforms, but the one which you use in thermos, or the covering of the geyser in your house is made up of ABS, which is a very hard polymer, right? And if you look at, for instance, ornamental things, like uh, if you have fake leaves or fake flowers which you use for uh, decoration, so that is very soft. And then you have folders, and then you have a lot of things around you which you can look and see that some of them are very hard, some of them are very soft, some of them are having different properties, so different colors, thermoelastic, elastomers, thermoplastic, and things like those kind of alteration you can do in polymer. Okay, so that is the one reason why it has dominated, and now the question is that it is causing a problem to the environment. And now people are looking for biodegradability of these kind of, so those polymers which are biodegradable will be having more advantage in comparison to others. But now the problem has, also for the environmentalists, the problem has become that it is very hard to replace the products made up from plastics which are non-biodegradable from the market, because there is no material which can replace it. Okay, steel being 100% recyclable. It is, so the only problem with the steel is in production, you are against environment when you produce it, because there is CO2 emission. But the product wise, it is completely green. So whatever amount of steel goes in the market, 100% is taken back and it is remelted and it is reused. Okay, but that is not the case with the polymer. But anyway, so that is why it gives you that advantage that you can use it in different applications. And so the point which I wanted to make was, if you look at a curve which looks like this at this scale of dimension, right? And then if I make it very small, so if I could make it very small, this curve will look like a straight line to me. If I could make it very small, so very small. So if I further can make it small, it will look like a dot, right? And similar is the thing which may look straight to you at certain scale. If you enlarge it, you might see that, that straight line is really not very straight, and things like that. So the thing is, it depends on the scale where you're looking at certain things, that the way they look. Similarly, the time dependence and temperature dependence of materials, it's not that in metallic materials you will not see it. It's just that the scale of time to see any time dependent deformation at the temperature we live in on this planet for metallic material will be very large in comparison to polymeric material. So it's just a difference in the scale. A polymeric material will deform even at room temperature. So if I apply a constant stress on a polymeric material at room temperature, then you will see the exact same creep kind of deformation which you would see in metallic material at elevated temperature. So if I load a sample which is made up of polymer, and if I apply a constant value of stress, then there will be an instantaneous elongation by which the length will change. And after that, the length will keep on elongating for the same amount of stress with time. As the time passes, this piece of polymer will keep on elongating. Okay. And this you will not see in metallic materials. You do the same thing at room temperature. So for why you will not see it? Because in order to see any significant amount of deformation in metallic material at room temperature, you might have to keep the same material for millions of years. And that we really see that, right? Because if you look at bridges, if you look at the structures which are made up of metallic materials in the world, which are very old. So you can have metallic structure which is 200 years old, 250 years old, and they have not elongated, they have not deformed, because the application of load has been constant, because that structure is there under its own weight, or it could be taking the weight of the structure which it is carrying, but it has not changed much in 200 years. So you see that the time dependent deformation in metallic material is insignificant at room temperature. But it doesn't mean that they will not deform. So if you keep it for a very long period of time, they will change their dimension. And you also, the other reason which you don't see in any differences in the bridges and other things, because the dimensional changes, so this delta L in metallic materials will be very, very small in comparison to polymers. And this you will see also in the stress strain diagram. So if you plot the stress strain diagram of a metallic material, it will go something like this, right? So initially there will be linear elastic deformation and there is no time dependence here. And then there will be yielding, there will be work hardening, and then there will be necking, and then there will be failure after some time. How would a stress strain diagram of a polymer look like? So one basic difference which we can say will be kind of general for polymeric material, that you will see this, okay? And then you might see this as well. And then you might see this and that, okay? Or what you can see is this and that. Do you understand the difference between the response of a metallic material and polymer materials? Do you understand why this difference is there, and what are the differences you can observe in the stress strain diagram of a polymer and a metallic material which I have drawn?
Yes, sir, because those chains basically they align, and then if they are all aligned, then basically breaking
So
those
before
chains
going to
requires.
the mechanism, can you tell me what differences are you able to observe between the two types of stress strain diagram?
Yes, sir. The curve first in for metals, the curve first increases linearly as per Hooke's law, and then after that it basically increases at an exponential rate, and after UTS it generally decreases. And for polymers, as we can see, it first increases to a maximum value, then it decreases, and then some it increases generally. But there is also a graph which basically shows that it's a straight line, not
Okay.
it's not increasing.
Okay. So it is good. What I find these days with the students, I'm not talking about you guys, that so usually I see this in the PhD comprehensive viva, is that when a question is asked, so try to answer the question in the briefest way possible, to the point, sometimes even the person who is asking the question may not be able to understand that, but that's a different case. So my question was that what differences do you see? You don't have to describe the whole path of the stress strain diagram. Just note down the differences. So let us take this diagram and this one. And can you tell me what difference do you see?
Sir, it attains a maximum and then it decreases a little bit, then it reaches to straight line, but
You are
in
describing the trend, Yatin. You're describing the trend. I'm not asking you the trend. Okay, so I will tell you what are the differences. And then you may appreciate that those are the differences which has been observed or not. So imagine that if I ask a 5-year or a student of 5th standard to note down the differences between this curve and that curve. So in my opinion, the differences which you can see, which you can appreciate is that one goes much higher in comparison to the other one, right? So there is a significant change in the slope here. Do you see that?
yes, sir.
Yes, sir.
Then the second difference is that there is a significant difference in the amount of total curve on the x-axis. Do you see that as well?
Yes, sir.
And the third one, which you were talking about, instead of saying that it increases and then decreases, I would say that there is a drop. And in the metallic curve, there is no drop. So there is one drop, obviously, after necking. So I can say that in metallic material stress strain curve, there is one drop. In polymeric material, there are two drops, right? In the stress strain diagram. So these are the three observations we can see, right? And obviously in this one, you also see another change where you have two drops and two places where the curve goes up, okay? Okay, so let us look at these differences. One difference, which is in the slope, defines that the stiffness of a polymeric material in terms of elastic modulus is much, much lower in comparison to metallic materials. And that you can, if you look at the values, you will be able to see that. So for instance, all the steels, some vary somewhere around 200 gigapascals, right? If you go to titanium, they go to 110 gigapascals. If you go to nickel superalloy, 170 gigapascals. Okay, so you are in that range. When you go to polypropylene, you go to 20 megapascals, sometimes 0.2 megapascals. So do you see the difference? So this is the amount of difference in the stiffness, and that's why you don't make bridges of polymers. So that is one place where polymer cannot replace. Okay, you can't make a railway wagon of polymers. You can't make, you can make wagon, but you can't make the wheel of rails of polymers. Why? Because of this. Do you understand? Do you really understand why elastic modulus is defining the structural ability? So
Yes,
we read about yielding and other things, yielding and work hardening and all those things. But all the applications of metallic material in our real world is actually just here. We don't want to go there. Never. We don't want the bridges to plastically deform. Otherwise, we will see bridges of different shapes. All the ships will be bent, all the cars will be having dents, right? So we don't want to see that. We don't want to play in this region. We do extensively study about that, but we keep our all products in the elastic region. And then why are we interested in increasing the yield strength? So that our elastic range increases. And why are we not playing in this region? Because then the next step is failure, right? The problem is that this is a monotonic curve, and you can still have failure even in the elastic region if you have cyclic loading. And that's why things fail, even in the elastic region. So why do we want to be in the elastic region? Because it is recoverable. And why are we using metallic material? Because the elastic range, the amount of force you can apply on a metallic material, and it will even then not deform plastically, is metallic material because of this high elastic modulus. Okay, so you can apply 20 kilonewton of force or 100 kilonewton of force, and then how much will be the so your stress is equal to elastic modulus into strain. And if you have so for instance, you apply 1000 megapascals of stress, right? And then how much strain you will be creating if you have 200 gigapascal? So you will be creating 10 to the power minus 2 of strain, right? Delta L by L is that. So if your initial length was whatever 1 meter, then delta L will be how much? 10 to the power minus 2 meter. Right? And now can you imagine, for the same amount of stress, if you apply on a polymer where your elastic modulus is 20 megapascals only, and then you're applying 1000 megapascals, so 1000 divided by 20, how much is the strain there? 50. So for 1 meter longer material, the delta L will be how much? 50. Do you see the difference? So this is why polymers have not yet replaced, and they can never replace. In the structural material, you can't make pressure vessels, jet engines, railway wheels, or these kind of things completely of polymers. You can't do that because the load bearing capacity, the structural capacity of polymers are not that high. What you can make is you can make utensils, you can make any other thing which does not require load bearing capacity. And that's where polymer play their role very nicely, that they also offer you that fine, if the load bearing demand is less, I offer you something free. And what is that? Lower weight. Okay. So elastic modulus difference is very significant. It is the most important thing you should look at when you are looking at stress strain diagram. And then you know the reason why it is going up and down, because of the alignment of all the chains are there. And there was this idea, I don't remember the name of the scientist who was studying polymer, and he said that he coined the concept of micromolecules. So one chain of polymer, he said that is a micromolecule, because that one chain acts like a molecule, right? So he is talking about number average molecular weight. But that idea was dealt with too much protest from the scientific community, because they found that the size of the crystal in a polymeric material was smaller than the size of the chain, which he was calling micromolecules. And that was the idea which was not, people couldn't digest, that a molecule can be larger than the crystal or the unit of the crystallinity, so unit cell kind of thing. But in polymers that can happen. You can have a very, very long chain which can sit in order and make a crystal, a crystalline part, a short range ordering. Okay. And then you can have, so in one local crystalline part, it can be formed of one chain, or you can have more than one chains as well. And you can also have situations where one chain is forming two short range ordered regions. That is also possible. So it is the deformation of polymeric material. If you want to have an analogy, then it can be said that if you have seen that bundles of wool which you use for weaving sweaters and other things, so so if you want to undo a sweater by pulling the wool from one side, then it is exactly like that. So it will keep on deforming without giving any, so it will keep on opening up. The wool will be keep on opening up as long as you're pulling it, as long as it is opening up and there is no obstruction there. But once you have opened, so for instance, you have a sweater, I don't know, I cannot draw a sweater, but you have some designs there, right? And then this is all, imagine that this is a sweater and then you have a small thread coming out here and then you start pulling this. So you will keep on pulling it, and then it will stop somewhere here because this part is discontinuous unless the chain continues to go in this part where you have made the design, right? So that will offer some resistance. And what if the amount of force by which you are pulling it cannot even go, so cannot even destroy the design? Then what will happen? The whole thread which has been aligned, now that will start elongating. So as long as you were opening up the thread and it was just getting opened up, it was going very smooth. As soon as it hit this design where you have to offer more stress and less strain is coming up, then you have a little bit of hardening there, right? And after that, this became aligned. So that alignment part will take some time. So a little bit of softening. Once it is perfectly aligned, and now this part is going to elongate, it will offer much higher stress, much higher resistance, because that is one fiber. And when you are pulling one fiber, what are you pulling? You're pulling one bond. And that is a covalent bond. So that has a lot of strength there. Metallic materials, they don't have very high bond strength. They are metallic bonds. It is very easy to break that. Covalent bond, very strong. Not easy to break them. So that's why you get a very high resistance when it comes to breaking of one chain, but it rarely goes there. Before that, it goes through a lot of deformation. And that's why if you have a tensile specimen of polymer, and if you test it, and you can look at the videos online, sometimes, so not necessarily every time it will show this behavior, but what will happen is that it will locally neck very fast. Okay. And then what will happen is that this neck region will keep on elongating. And the amount of strain which we are talking about in polymeric material, you remember this curve? We are talking about 200, 300% of elongation. In comparison to metallic material, you have 20%, 10%, 15%. So we are talking about huge elongation there, which you have seen in some of the plastics, which is used for that property, that it can elongate much. So you have those elastics, and rubber, for instance, is used for that property because it can elongate to a very, very large So the amount of delta L it can have is even longer than the amount of original length it has, meaning it is higher than 100%. Okay, so that's the advantage which metallic materials cannot offer at all to you. It cannot even reach 100%. And that is one place where you have to also think that the theory of small strain which we used in metallic materials, so the definition of strain which was this, and del U J by del Xi, this is no longer valid in polymers, because you will have to take higher order terms also, because these terms will be also significant in case of polymers. Okay, so Green's strain is no longer the defining strain in polymers. Okay, so that was something, and then very similar but not exactly similar to the kind of damage which you have in ductile materials. So we have discussed the formation of small voids, and then they grow and then they join together, and that constitutes the ductile material, ductile damage of your metallic material. By the way, from this, I hope you guys are preparing for your project work in MM311. So before semester, we will have a presentation, okay? And that presentation, I'll tell you the date of the presentation, and we have to do it very soon, maybe next week or so. So I have told you about that. So you have to present your idea and solution for that topic of ductile damage, right? Okay. So in polymers, what happened? The plastic deformation can happen because of two mechanisms. So one mechanism is called shear band formation or shearing, and the other mechanism is called crazing. And crazing is something which you can see yourself. So you take a balloon, and when it's don't blow it, so just tear it apart, and then a small piece of balloon, try to stretch it with your two hands, and you will see that the color will be changing. You can also do that if you have a big piece of rubber, if you can elongate that. So you will see that in certain areas, the color will be changing, a whitish color will appear. And then from that, you will see small holes coming up. You will see that. You can do this at home, and you can really see this. You will see small holes coming up locally, exactly like micro voids, right? And they will not, yeah, they will grow, and then they will join also. But the whole deformation is looks same, but the whole thing is different, because there is no unit cell in polymers, and there are no dislocations and things like that, and they deform in a completely different way. But you will see similar things in polymers as well. So what happens is that you will have this areas where you have these hole, which will be, so you will be seeing all the holes which will be forming perpendicular to the applied maximum principal stress, and the molecular chain which is surrounding these holes will be aligning themselves in the principal direction. So they will have a tendency to align their chains in the direction of the, so if it is a uniaxial tensile test, then they will be aligning themselves in the direction of the stress or the force which is applied. Okay. And these holes will be growing, and after that, they will join, and the thing will break. And this phenomena of this kind of hole formation is called crazing. So the first stage is not the hole formation, but first stage is that the color change starts occurring, And then the next thing you see is that, so how this happens is by formation of microfibrils. So basically you have a crystalline structure or a combination of crystalline and so you have a lot of things here. So you have crystallites like that, and then you have loose areas where you have a lot of chain which is kind of amorphous and just sitting there, and it depends on the degree of crystallinity, how much part will be like that and this and that. So this is how it is. And then when you start pulling it, so the chains are being pulled. So what happens sometimes is that if you have, let us say, a lot of area which is amorphous in the or glassy in the polymeric structure, because of the application of stress, they get sufficient energy to crystalline these parts also. Sometimes that also happens. So the amount of crystallites increases uh, because of stress application. And when that happens, then you will have more resistance to deformation. Okay. And in other cases, what will happen is that these amorphous region will deform, and then they will put the stress on the crystallites, and that crystallinity will break and they will become open. And when everything is opened up, they will try to align themselves. And when they align themselves, then these holes will appear. Okay. So this is how they deform. And so I think we can stop the session here. And do you have any question to what we discussed today? Are you guys there?
Yes, sir. Sir, your voice is breaking slightly.
So was it breaking before or is it breaking just
Okay.
now?
Not before, sir.
Okay. So just a second. So are you able to hear me?
Yes.
So do you have any question?
No, sir.
Okay. So I will end this session here, and I will also share the other lecture for this week, and we will have the other lecture for MM308. When are we having that? At 3, yeah?
3, sir.
Okay. So we'll meet at 3 p.m. again for a different course. All right. So we end this session then.